Dimensionality reduction. In a multilayer perceptron, if the number of hidden units is less than the number of inputs, the first layer performs a dimensionality reduction. The form of this reduction and the new space spanned by the hidden units depend on what the MLP is trained for. If the MLP for classification with output units following the hidden layer, then a new space is defined and the mapping is learned. To minimize classification error, see figure 11.18. We can get an idea of what the MLP is doing by analyzing the weights. We know that the dot product is maximum when the two vectors are identical, so we can think of each hidden unit as defining a template in its incoming weights, and by analyzing these templates, we can extract knowledge from a trained MLP. If the inputs are normalized, weights tell us of their relative importance. Such analysis is not easy, but it gives us some insight as to what the MLP is doing and allows us to peek into the black box. Figure 11.18 shows that OPT digits data plotted in the space of the two hidden units of an MLP trained for classification. Only the labels of 100 data points are shown. This MLP with 64 inputs, 2 hidden units, and 10 outputs has 80% accuracy. Because of the sigmoid, hidden unit values are between 0 and 1 and the classes are clustered around the corners. This plot can be compared with the plots in Chapter 6, which are drawn using other dimensionality reduction methods on the same dataset. An interesting architecture is the auto-associator, which is an MLP architecture where there are as many outputs as there are inputs, and the required outputs are defined to be equal to the inputs, see figure 11.19. To be able to reproduce the inputs again at the output layer, the MLP is forced to find the best representation of the inputs in the hidden layer. When the number of hidden units is less than the number of inputs, this implies dimensionality reduction. Once the training is done, the first layer from the input to the hidden layer acts as an encoder, and the values of the hidden units make up the encoded representation. The second layer from the hidden units to the output units acts as a decoder, reconstructing the original signal from its encoded representation. So figure 11.19, in the associator, there are as many outputs as there are inputs, and the desired outputs are the inputs. When the number of hidden units is less than the number of inputs, the MLP is trained to find the best coding of the inputs on the hidden units, performing dimensionality reduction. On the left, the first layer acts as an encoder, and the second layer acts as the decoder. On the right, if the encoder and decoders are multilayer perceptrons with sigmoid hidden units, the network performs nonlinear dimensionality reduction. It has been shown by Borlard and Camp 1988 that an MLP with one hidden layer of units implements principal components analysis in section 6.3, except that the hidden unit weights are not the eigenvectors sorted in importance using the eigenvalues, but span the same space as the H principal eigenvectors. If the encoder and the decoder are not one layer, but multi-layer perceptrons with a sigmoid nonlinearity in the hidden units, the encoder implements nonlinear dimensionality reduction. Hinton and Salahatdinov in 2006. Another way to use an MLP for dimensionality reduction is through multidimensional scaling. In section 6.5, Mao and Jiang in 1995 show how an MLP can be used to learn the Zeeman mapping. Recalling question 6.29, Zeeman stress is defined as the follows: that the expectations of sigma conditioning x is equals to summing for all pairs of R and S of the square of the following terms. That is the norm of g of x to the R conditioning theta minus g of x to the S conditioning theta. Such a norm minus another norm, that is x to the R minus x to the S, is norm, then divided by, and this is by normalization, divided by the same term, that is the norm of x to the R minus x to the S. An MLP with D inputs, H hidden units, and K less than D output units is used to implement G of x conditioning theta, mapping the D-dimensional input to a K-dimensional vector, where theta corresponds to the weights of the MLP. Given a data set of x which is equal to the set of x to the t, where it contains all possible t, we can use gradient descent to minimize the Zeeman stress directly to learn the MLP, namely g of x conditioning theta, such that the distance between the k-dimensional representations are as close as possible to the distances in the original space.